Do you guys have any questions about anything? Yeah.
If you pass like an array into a recursive function and you want to pass it like using the address, like a wheel, do you need to dereference it at the beginning of your recursive function?
So like you're trying to pass in like array plus 5, something like that, or like are you just trying to pass in like AR and AR is an integer pointer?
Like it would be like if you're doing it in C++, it would be like reference to the array.
So you want to pass in, you're saying your question is, do you want to pass in a reference or do you want to pass its address? So references in C++ are essentially hidden pointers in terms of implementation details. So what you'd want to do is, again, try to write your code in C because it gives you a better corresponding to the assembly. So here you would just pass in probably, if you wanted to, I guess it depends what you're planning on doing with the array. If you're planning on modifying just the elements inside of the array, you could just pass the pointer itself. So if you have an array of integers, right, called AR, and you'd like to modify that, the elements inside of the array, the actual values, you can just pass an AR, the integer pointer. That's fine, right? But if you want to modify the integer pointer itself, like you want to resize the array, you'd have to pass in an integer pointer, and then pass in the address of AR to your function. Does that answer your question? Okay, anything else? So we're going to pick up on the inline assembly code from where we left off on. But before we do, what are the GCC C calling conventions? What's at least, just give me one of them. The prologue and epilogue aren't part of the actual calling conventions. They are normal things that will be done just because it makes writing the functions, though, easier. Yeah, so the return value is going to be in EAX. The arguments are passed on the stack. In what order are they pushed? Yeah, they're pushed right to left. And then what's the third rule? So it depends what you mean. Which function? The calling function or the called function? The calling function is responsible for saving A, C, and D. The called function, the one that's actually getting called, so function 1 calls function 2, function 1's the one doing the calling. Function 1's responsible for saving A, C, and D if it's using any of them. And then function 2, the one being called, is responsible for saving all of the other registers that it plans on using besides those three. Again, it's really important that you follow these conventions because if you don't, your code won't work. It'll break. Right? It's just like driving on the right-hand side of the road or the left-hand side of the road. It's not going to work out so well. Right? Things are going to break down. Okay, so last time we left off, right, we talked about the basic format of the inline assembly code. It's underscore underscore ASM underscore underscore to get started, right? There's 4 sections. There's the text section, there's the output section, there's the input section, and then there's the clobbered section. Each of these sections is optional, so you don't have to provide them if you don't want to. But you can also, if you want to leave a section blank, you just put a colon in that spot and then move on. Notice the spots are separated by colons to separate each of the fields. Remember the code that's in the input section, right? Whatever's in here, before the inline assembly code will be run, the compiler will copy whatever you say that you want to copy over here in C land over into this location in the assembly, G being general. The compiler figures out where it's supposed to go. And this is how you can refer to it inside of the inline assembly code, right? Then your inline assembly code will run. And then after it's done running, the compiler will run the output section, which will take what's in the specified register, right? Who you'll talk about inside the inline assembly code with this name, and copy it back out to this C variable, right? Do you remember what the plus means? It's both input and output, right? So before the inline assembly code is run, right, we'll copy that value in, copy the value A into wherever register the compiler decides to pick, and then after the inline assembly code is done, whatever in this register will be copied back out to A. Right? Are there any questions on the basic format so far? Probably the ones you're going to write are going to look a little bit more like this one. But are there any questions here about what any of the parts mean or what any of the parts do? Right, and remember, instead of the plus, the other thing that you can put in the output section is the equal sign, which just means the result will be placed, whatever's in this register at the end of the day will be copied over into this C variable after it's done running. The final thing that we have to talk about in terms of the modifiers you can put on the register specifiers is the ampersand. So the ampersand stands for early clobber. Now, what this means and what it does is really important, but we have to first understand what assumptions the compiler is going to make about your inline assembly code in terms of the outputs and the inputs. So the compiler makes the following assumption, right? You will not write to any outputs before you are done using all of the inputs. I'll say that again. The compiler assumes that you will not write to any of the outputs before you are done using all of the inputs. Does this make sense in terms of this assumption, right? So again, this means before we put anything into result, right, we have to be completely done using, let's just say, before we put anything into this register where results sort at, we have to be finished using whatever we're using this register A for and whatever this register B for, right? Once we're done, then we can write to the results. Now, some of the assembly code that we write might not make sense to follow that assumption, right? So if we look over here, notice, am I following that rule? Am I keeping to the assumption that the compiler is making about my assembly code? No, right? Because I wrote to the output before I was done using all of the inputs, right? So if you ever do this, if you ever write to an output before you finish using it or before you finish using all the inputs, you have to mark it early clobber to let the compiler know that you're not following the convention for that register. So since I write to result before I am done using all of the inputs, I have to say that result is early clobber. Does that make sense when to apply it? Right? So if you write to an output before you're done using all the inputs, you must mark it as early clobber. Right? A lot of people still get confused by that. So if that statement doesn't make sense to you or how you can recognize when that's happening, let me know right now so we can clear that up. Okay, so again, the compiler makes the assumption that you will not write to any output before you're done using all the inputs. And under this assumption, it can do something called register sharing, where it maps both outputs and inputs to the same register, right? This is legal for the compiler to do because you won't write to the output, you won't treat it like an output until you're done using all the inputs, treating it like an input. Does that make sense? So again, the compiler is trying to optimize the register usage. So under its original assumption, again, that you will not write to the outputs before you're done with the inputs, it can have an output and an input mapped to the same register. So what might happen is the compiler might decide that for maybe B, it wants to put B in EAX, right? And it might decide that it wants to put A in EAX. Let's just say A goes into EAX and B goes into EBX. Keep things simple, right? Now, if I don't mark this early clobber, right, the compiler can decide to put either result into EAX or result into EBX if we did not mark it as early clobber, right? This might cause some problems, right, if this happened. So again, imagine this isn't there. Let's say that result is, say, EAX. So over here, and then A is EAX. Well, here we put 0 into result, right? But result is what register in our example? EAX. But what's our input register also? So what just happened to your value A? You got overwritten with the value 0 and it broke. Right? I'll show you this actually happening. But I just want to make sure. Are you guys clear on when to apply the early clobber? Because everyone every year always gets confused. Okay then. Hopefully you guys don't make the same mistake. So I'll try taking this out and I'll show you it breaking. So over here, G++ basic inline.cpp. So it compiles and we run it. And all of them are doing 100 plus 10 in terms of what they're doing. So they're all trying to add 110. And notice that all of them work except for the last one. The very last one is the one with the clobbered register. And here you can see why. If we do G++ dash S and then the inline, oops, what do we call the basic inline, right? G++ dash S basic inline.cpp, and then we jet it basic inline.s, and then we turn on the highlighting so we can all see it a little bit better. So one thing to note is that the compiler does something called name mangling in G++ that's not being done in GCC in terms of like the C code. Because remember in C, how many functions can you have that have the same name? Just one. So in C, each function has to have a unique name. In C++, what's the limit on the number of functions that can share the same name? There isn't a limit. Multiple functions can have the same name. The limiting factor in C++ is what? What has to be unique for a function? It's signature, right? It's combination of name and parameters, right? So the way that the compiler actually does the translation into the labels is that it kind of adds the information about the arguments in there. So this is ABC add II, integer. Right? So it's going to do some messing up with the names so that each of the label names ends up being unique for each of the functions. So that's just something to point out, something cool to notice. So let's go to the clobbered add. So over here, this app, no app, this is where our assembly code is being done. Right? This is our inline assembly code where the compiler decided to insert it. And I'll knock it on different lines so that it's a little bit easier to see. So over here, here's where our basic inline function is going to be. So here we moved 0 into EAX, right? The first line of our assembly code that we said to do was to move 0 into result. So what register did the compiler decide to use for result? EAX. Now if we look over here, we then move EAX to EAX. And then down here we said move %B to result. So what register did it choose to use for B? EAX, right? And then the next line of code was move EDX to EAX. So the compiler must have chosen EDX for A, right? But notice it used, like we said, they had the problem happen where it picked the same register for the output and the input because it's trying to share registers because there is such a small number of them, right? And it's not working because we broke the assumption the compiler had that we would not write to the output before we finished with all of the inputs. Does this make sense? Why it's breaking? So when you mark something as early clobber, right, you tell the compiler, hey, I'm actually going to be writing to this output before I finish using all of the inputs. And so what the compiler has to do is give it its own separate register to be in. So if we recompile, we get 110, and then if we recompile the assembly code, and then we go back to clobbered add, and now we go over here to our assembly code. Notice the compiler was forced to pick different registers. Now result is EAX. Over here we have EDX. EDX is going to be B. And then ECX is going to be A. So now we don't have this problem of there being that register sharing and we accidentally overwriting the input. Does this make sense? Are there any questions about writing inline assembly code? Yeah.
So you're saying that there's like a text output input forward section, but like I can't.
Okay, so here's the code section. So everything up until here's the code, and what marks the delimiters are these colons. So notice we have code, colon, output, colon, input, colon, and then the clobbered section.
We're going to the semicolons for inside the section, lines inside the section.
So the colons denote the sections, right? There's 4 sections, like the assembly code, outputs, inputs, clobbered, right? And the colons denote like kind of like the end of the section. So you put all of your assembly code down, and then a colon in some place to mark the end to move on to the output section. You list your outputs, colon, then your inputs, colon, and then your clobbered section. Colons inside of the strings separate the lines of code inside the assembly so that we actually get legal instructions. If you forgot to put these semicolons here, your code just wouldn't run. Yeah.
So you said something where it's you have to mark it as clobbered. If you don't mark it as clobbered, does that mean that compiler always does the most efficient thing and just try to save as many registers as possible?
So if you don't mark a register as being early clobber, yes, the compiler will attempt to be as efficient with the registers as possible and do the register sharing. Again, you have to mark an output as early clobber, right? If you write to that output before you finish using all the inputs, right? And like the easy way to know that is you write your assembly code and you look at where you write to your outputs. And you're like, well, I did this right to my output. I look at the rest of my assembly code. Am I using any of my inputs? Right below that line. If your answer is yes, I'm still using some of my inputs, that output's early clobber and you're done, right? It's really easy to recognize in terms of like what needs to be done because you just watch the assembly code. Like down here, right? I wrote to my output. Do I reference any of my inputs below this line of code? Yes, right? On line 111 and 112. Therefore, result has to be early clobber to work. Right? That's just the way to do it. So you can start with them, none of them being early clobber, and then just look at the code that you write and figure out from that which ones need to be set to early clobber. You don't have to mark any of the ones that have the pluses as early clobbers because they're inputs and outputs, so they're already being reserved for that one use, and they can't be shared, right? Because you already said what's supposed to go into it, right? Whatever the input's supposed to be, and then the output will be placed in the same register. Any other questions? Okay, let's talk about some additional instructions then. So again, there may be some times where you would like to reach for the inline assembly when you want to use some special instructions. Where are my special instructions? So some of these instructions the compiler would never use. They're called string instructions, just to give you an example of something the compiler wouldn't use. And they do a couple of different things. There's really 3 of them. There's moves, so move string. There's stos, store string. And then there's comps, compare strings. And they each do something a little bit different. What the moves section is going to do, it's going to take whatever is an ESI, right? So go to that location in memory where ESI is pointing to, and it's going to copy it to wherever EDI points to. So notice we're moving something from memory directly to somewhere else in memory without having to specify an intermediate register. which is pretty nice sometimes if you need to do, like moving arrays, right? Moving the contents of one array to another array, like doing an array copy. It will then decrement ECX. Then there's something about the direction flag. If the direction flag is set, then EDI will be decremented by 1. Otherwise, EDI will be incremented by 1. Same thing for ESI. So if direction is set, you'll do -1. And if direction is not set, it's currently 0, you'll go +1. You'd want to set the direction flag if you want to do things in reverse. It's like go from right to left. So that's all the move instruction does. And the only thing that's really different is about the size of the things that you're moving, right? Move a byte, move a word, move along. And therefore, like EDI and ESI have to be incremented by 1, 2, or 4, depending on whether you're moving a byte, moving a short, or moving like an integer. Yeah?
What's that C?
Oh, it's the contents in memory. So this is like a notation that Professor Matloff used in his book. So it's memory at location EDI is equal to memory at location ESI. Are there any questions about what the moves instruction does? Then there's the STOS instruction, which will take whatever in EAX and then copy it to wherever EDI points to. Right? Go copy that value in there, and then again, ECX will be decremented, and then EDI will be either be incremented or decremented based off of the direction flag. And then comps can be used to compare two things in memory. So what comps will do is it'll do a subtraction. It'll do whatever in ESI, right, that location of memory at ESI, minus the location in memory at EDI. Subtract them two, and again, incrementing and decrementing of EDI and ESI, and then ECX always goes down by 1. And then there's the SCAS instruction, which is like the string compared to like literal, or compared to a constant. So over here, it'll always do like essentially EAX minus the contents of EDI for doing the comparison. And then again, ECX goes down by 1, and EDI will go up by 1 or down by 1, depending on whether you have the direction flag set or not. So it seems kind of weird, right? Like, why is ECX always being decremented given that you're just comparing two things or moving two things? Generally, these instructions aren't used by themselves, but they're used with the repetition prefixes. So in front of each of these instructions, scroll down, you can put some of these optional prefixes. So you can say rep moves, or stos, or rep stos for the instruction. Or there's also repeat, repeat with equal, or repeat while not equal, which you can do with the comps and the SCAS instructions. And what the whole point of those instructions will do is they'll keep repeating, the rep ones will keep doing the instruction over and over and over and over again until ECX reaches 0. Right? So if you had two arrays that are supposed to be the same size, maybe they're like 10 long, right? So you could say put into ECX the value 10, because you want to copy 10 elements, put your destination into EDI, the pointer to the array that you want to copy things to, put your source into ESI, right, where you want to copy from, and then just do rep moves with the appropriate suffix to copy the entire array, instead of having you to write that manual little loop yourself to copy each element. Does that make sense? Any questions so far about these instructions before we show you some examples of using them?
So you have to manually store the result in your register if you choose one.
What do you mean for the result? Because all the results in some ways kind of go to memory, at least for the moves and the STOS, right? They move something into memory, whereas the comps and the SCAS are comparison instructions. So you would check like the E flags afterwards. So after you did like a comps or a STOS, you probably have like a jump if greater than or jump if less than.
But like if you're moving in, like where can you set where you're moving to?
So EDI is the destination, right? It's the pointer to where in memory you want to copy the result to. So right, so if you wanted to copy your results to location 100 in memory, you would set EDI to be 100. If you wanted to copy from the array beginning at location 500, you'd set ESI to 500. The one thing that's a little bit interesting about the comps and SCAS, right? They'll keep going. Like if you do the repeat while equal or repeat while not equal, repeat while equal will keep comparing the values until either ECX reaches 0 or the values stop being equal, right? It'll keep comparing them while they're equal, right? Or until ECX becomes 0. So it'll stop either when ECX becomes 0 or there's a difference between the elements, right? Whereas repeat while not equal will keep going while the elements are not equal to each other, so it stops on the first difference, or when ECX reaches 0, whatever one happens first. Now the problem that you might have here is, well, how do I know if I got to the end, right? Or if there was a difference between the elements, if you were doing, say, like repeat while equal, right? Did I stop because they stopped being equal, or did I stop because ECX reached 0? So what you can do, scroll down, come on. So there's another jump instruction. It's JECXZ, which is jump if ECX is 0, which will only be true if ECX is 0, right? So if that one's 0, it means you reach the end, right? ECX became 0. And then the jump if 0 or jump if not 0 or jump if equal or jump if not equal, you would use to test to see if you stopped for the elements either being equal or not equal, right? Because you don't know why you stopped after you stopped, just that you stopped. And this is how you can tell the difference, right? The JE or JZ or JNZ or JNE, right? You can use for the equality checks, right? This will help you figure out if you stopped that they were not equal to each other or equal to each other, depending on what suffix you were using. And then JCXZ can be used to figure out if you reach the end. Does that make sense? So I now have questions for you. Can you think of any things that can be useful to use these instructions for? Arrays. So what do you think moves would be useful for? Copying arrays from one location to another. Do you guys know what the name of the built-in like C library function that does that? Not string copy, because string copy copies strings, right? It's memcopy, right? What memcopy will do is it'll copy like X bytes from source to destination, which sounds like you could implement it really easy with this instruction. What about stosb? What do you think it would be, or like any of the stos instructions, what do you think it would be useful for? Given that it's going to change the contents in memory to whatever's in EAX. Well, we're not copying what? We're not copying arrays, right? Because the stos instruction, it just takes a single value and it places it in that location in memory. Yeah, filling an array with some constant value. Right? Maybe you want all the elements in your array to be 0, right? You could use stos for that, right? You want all the elements in your array to be 10, you can use stos for that. It's whenever you want to fill some section of memory with the same value, right? The instruction that does that, oh gosh, what's the one that does that in C? MemSet. So it's like the MemSet function where you'll set the elements in memory to be one constant value. But MemSet, be careful with it if you do use it later on in your programming life because it sets bytes. Change X bytes to the value that you specify. So if you tried to say, well, I want every element in my array to be 10, right? And you have an array of integers, you could not use MemSet and say, okay, set all, the size of my array times the size of an integer to 10, because it'll set each byte to 10, right? And so those 4-byte quantities will not be it'll be 10, 10, 10, 10, 10, but that'll be interpreted as one integer, which is not 10. So it wouldn't be filled in correctly. What about comps or SCAS? What do you think they could be useful for? Well, not that the arrays are the same size, right? Because before you would even compare the arrays, you'd have to know their size, right? If you didn't know the size of the array ahead of time, you couldn't compare the elements correctly. What else might they be useful for? Because again, remember now you also have these other prefixes you can use. You can use repeat while equal or repeat while not equal. So keep doing the comparison while things are either equal to each other, or keep doing the comparison while things are not equal to each other. What does that mean? We have to know when to stop. Because remember, like the comps and the scats, they don't copy values, they compare values. Right? They just keep doing the comparison either like while they're still equal or while they're not equal. Right? And then the comps will be comparing two strings or like two arrays at the same position, right? Whereas SCAS will be comparing a constant or like a fixed value with the elements in an array. But move inside the array to what? But you already know where the end of the array is at, right? Because you have to know the size, right? Because if the size of the array was 10, right, you can just do array plus 9 and get to the end, right? No need to go through the elements in between. Check if two arrays have the same values, right? If you knew the size of both of the arrays, right, you could do a repeat while equal, and you keep going through the elements, comparing them while they're equal, and you want to stop when you reach the first occurrence that's not the same, right? So you repeat while equal, and then you check, well, if ECX is equal to 0, it means the arrays are the same. But if the ECX is not equal to 0, right, it means the arrays are different. Right, because you stopped before you reached the end of the arrays, because you would load ECX with the size of the array first. What about, that's how you could use comps. What about the SCAS, comparing it with a constant value? You could see if the element is in an array, or figure out where the element is at in the array. Right, those would be some uses for it. And aside from those uses, I have not been able to think of another single use for those instructions. Right, so I think it's kind of sad that there's like actual dedicated hardware for essentially accomplishing one function a piece. I cannot think of any other way of using it. So let's show you some examples of me actually using them. Inline fun.cpp. So here's the first one, which is the MemSet, right? Which I said what it does is it fills in some section of memory with this value, but it fills in that. It fills in number of bytes beginning at pointer with value, where value is 1 byte big. Does that make sense? So we want to fill num bytes starting at pointer with value. So what I do is, here's my inline assembly code. So I clear the direction flag. So there's CLD, which clears the direction flag, and there's STD, which is set the direction flag. And so this will control which direction you're going. So I want to clear the direction flag so that I move forward just in case it happened to be set. And then all I do is rep stos b, essentially one single instruction. The reason that this works is before my inline assembly code runs, right, in the input section, I put pointer into EDI, I put my value into EAX, and I put the number of elements into ECX. The condition codes will actually change because I'm changing the direction flag, and the contents of memory will also be modified because I'm changing what's there. Are there any questions about this little small guy and how it works? Yeah.
Can you explain like ECX and how that's gonna change, but how that works when you're running the rep?
How does ECX change?
Yeah, like because num is supposed to be
The number of elements you'd like to copy?
right. So when you're running rep, you're checking so that that's 0 or
Yeah, I mean, like the rep instruction will keep the rep prefix will keep redoing that instruction until ECX becomes 0. And notice that each one of these instructions, what do they do each time? They also decrement ECX, right? So they're really designed to be used with the rep prefix and not really designed to be used standalone, though they can be, and I'll show you an example of that in a minute. Yeah.
Could you please clarify why you use size T for the type of ground instead of
That's what I used, size T, because that's what the documentation online said was the signature. Sometimes you're going to have issues when you're going across different machine sizes about like what the size of the variables are. For example, is your integer going to be 32 bits big, or is it going to be 64 bits big? Yeah, there are. It depends. It'll be like a fixed size quantity, which you can like look up online. And there's also ways of specifying like how big you want your integers to be. Like you can do like uint underscore 32 for an unsigned integer that's 32 bits, right? Or uint underscore 64 for a 64-bit integer. When those size issues matter, right? To make your code more portable and work on more platforms. Mm-hmm. So here's memcopy, right? This is what like memcopy would look like if you wrote it as a loop, right? This is like the assembly code, right? First we make ECX, our counter, be equal to 0, right? Then we compare size with ECX, right? While ECX is less than size, jump if it's greater than or equal to, get out of the loop. Then we'll move whatever's at source, right? ECX past source, so source at I goes into BL. Then move BL to your destination, increment ECX, and then go back to the top of the loop and do it again, right? If you actually wanted to write all of that inline assembly, right? And I don't have any outputs in my output section because I'm only changing memory. And then again, I said, hey, compiler, you can choose where source goes, where destination goes, and where size goes. And I'm also going to be changing ECX and EBX on my code. Notice ECX changed here, EBX changed here, but they're not listed as either inputs or outputs, so I need to make sure that I do that. Also, memory changed, and then E-flags changed too. This seems like a lot of work, right? Well, here's the version if we use SCAS. Or not this, the SCAS, moves. That's pretty short, right? We're reusing the instructions that are there, the specialized instruction. So again, we just make EDI be our destination. We make ESI be our source. We put put our size into ECX. Then we do rep moves B. It copies everything over for us, and we're done. Any questions about this version? Yeah.
So where in memory is the answers?
Somewhere in, I mean, like technically in memory, the answer will be stored at destination. At dest, right? But here you're just telling the compiler that memory changes, because what the compiler might be doing is it might be caching values from memory in registers, right? Which you guys have probably been doing when you're writing your own assembly code, right? You say like ECX is going to be I, and you keep using EAX or ECX as I the whole time, right? Instead of that location of memory that you reserved for I. So because you've changed something in memory, if the compiler was caching anything in certain registers, it's going to have to go refetch those values from memory to make sure that they're still up to date in case you change them in the assembly code. Does that make sense?
So like right after this function, you can start indexing dest and it would have all of that stuff.
Yeah. So here's contains. It's a little bit longer, right? So at the beginning, we're going to put elements into EDI, put the value that we're looking for in A, and then we're going to put size into memory somewhere. So here we're going to move size into ECX. It's our counter, just again, show you that happening. And then we'll do a repeat while not equal with SCAS, but notice it's SCAS L. Keep comparing values while they're not equal, right? While they're not the thing that we're looking for, keep going. We're either going to stop when either ECX is 0, right? Or when the things are equal to each other. So we'll jump to ECX. You know, if ECX is 0, that means we didn't find it, right? We went all the way through the array and we stopped because ECX was 0. So go to not found and put -1. We didn't locate the value into index. Otherwise, right, we're going to put size into index that's where we kind of found it at. But put size into index and then subtract out ECX. We kind of need to do, because we searched, ECX kept getting decremented, and so we need to figure out how far we moved. So you have to do subtraction to get the amount that you moved. Or what might be somewhat easier is if you did it in reverse. Then ECX would just have the position that it found it at. Right? Because if our array is 10 big, right, and we find it at position 2, ECX will be 8 because ECX started as 10. It wasn't at 0, so we went up to 1, right? It wasn't there, so we went to index 2, so we went down to 8. 10 minus 8 is 2, so it was at index 2. That's why the subtraction's there. Put that into our index and then jump to done. Any questions here? In the clobber, use ECX. So one thing that I tried to do was I tried to do stir comp using the compare strings, the comps string function for doing that. And what I thought I could do is I could put ECX as being infinity. So make it the largest possible number ever, right? And I'll keep going and I'll go until the end. And if I get to the end, well, great, they're the same. But if I find a mismatch, well, they won't be the same, so they're done, right? The problem with doing this is if you compare a string with itself, they're going to start at the same location in memory. And how long will they be the same for? Forever, because you're starting at location. Both start at 100. Well, 100 is equal to 100. 101 is equal to 101. 102 is equal to 102. And so you write yourself an infinite loop. So for this one, I believe I had to, is this like the recursive function? No. Over here, I just used comps b to compare it, but notice there's no rep prefix. So I would just compare, and then if they're not the same, great, we're done. Otherwise, we'll move forward by 1 automatically. But I need to have more finite or more fine control over what was happening than just say, keep going while they're equal or keep going while they're not equal. So there's some examples of using some instructions to do some things. Again, there are a lot of other built-in instructions in the Intel hardware. It's called a complex instruction set because it has a lot of different instructions in there. But again, the compiler doesn't use most of them. So one of the reasons you might use the inline assembly code is because you need access to one of those special instructions. For example, there's an instruction in there that does encryption of values. And it's much easier to use the encryption algorithm that's built into your hardware because you know it's 100% correct and you don't have to re-implement it. And it has all the security features that you need and it's well tested. And so you can just invoke that instruction on it to encrypt your data instead of having to actually write the encryption algorithm yourself. That's it for assembly code. Do you guys have any questions before we move to our next topic? Okay. So now we're going to move and we're going to talk about the operating system and all the nice things that it does for you. So the first thing that I want to let you know is the OS is a program. So just like all the programs you write, the OS is just a program, right? A large, complex program written by a lot of people, but still a program, right? What do you think makes the operating system, though, be special? More special than your programs? because the OS can do certain things that your program can't. What's your guess? Well, I mean, well, you can write the files too, right? That's all it means, that it means to be written permanently. You just write to the hard drive, right? And your programs themselves, they're also stored on the hard drive when they're not running.
Seems like OS had a priority access because it can direct traffic between different.
Yeah, it definitely can direct traffic, but like, what gives it that special privilege? Why can't you do that in your programs? It's only special because, if I knew how to spell special, it is the first program run, right? So when the computer turns on, right, the operating system turns on, it's going to start, or the computer turns on, it's going to start running the operating system. Now the operating system, when it's running on the CPU, will have access to all the special permissions and all the special functions. But when the operating system goes and runs your programs, it turns off all the special permissions. So it's like, no, you don't get that. And because it's the first one that's run and it controls, who else gets run and with what permissions, it can turn those off, right? If your program was the first program run, it could do everything the operating system does, right? And it would have all those special privileges as well, right? So a question to you is, assuming only a single CPU with a single core, if your program is running, is the OS running?
Yes.
So how many of you guys think the OS is running at this point in time? How many of you say no? For those of you that say no, why do you think not? Okay, let's do this analysis. So how many programs can a single CPU with a single core run simultaneously? Just means that there's no parallelism. So how many programs can it run at once? One. So if your program is the program that's running, that's one program that's running, which means what? That's the program that's running. So can the OS be running if your program's running? No, not under this situation, right? Which should hopefully make sense, right? But even in these circumstances, you've seen that things can actually be running at the same time, or the operating system can take control, right? So how can control between programs change? What do you think are the ways that the control between programs can change, right? Or control over the CPU, how can that change? Yeah, but I'm running right now, right? How can we make sure that control switches between me to somebody else? How could that happen? Like, imagine you're back in daycare, right? And there's a favorite toy that everyone wants to play with, and you're playing with it right now. How can the next person get access to that toy? You can just give it to them, right? So you could voluntarily relinquish control, right? So whenever you do a system call, you're saying, hey, I would like to stop running, right? Somebody else, please run instead, right? Generally, when you're saying the other person to run, you're saying, operating system, please do something on my behalf when you're doing a system call, right? So what are some other ways that control could change besides you give that toy to somebody else? What? Well, they take it, but let's assuming like, the other children are incapable of taking it. Who else happens to be at the daycare? The teacher could take it, right, and give that toy to somebody else, right? The other way that this kind of happens is that the hardware can interrupt the program that is running, right? So when I'm typing like my keys, it'll interrupt the program that's running, and it will cause some other program to be run instead. Just make sure I got all that stuff right. So if you're looking at for like where we're at in the book, we are now in chapter 9. Okay, good. Got all those things itself. So one other question before we move on is, what does it mean for your program to be running? How would you know that it's actually your program running right now and not some other program? So what does it mean for a program to be running? How can you tell what program's running? Well, yeah, you can see it, but like how looking inside the computer could you know which program is running? Yeah. Well, I mean, like your program's is running, right? So you're saying, but we're trying to figure out how our program is the one being run. So you could say you're saying that if ESP is pointing to the stack that belongs to our program, then our program is running. You could probably go with that. What about EIP, the instruction pointer? I would say like your program is running if EIP is pointing to memory belonging to your program, right? Because EIP controls what instruction is being done. And if EIP is currently pointing to one of your program's instructions, your program must be the one that's being run. Does that make sense?
So you're saying you could have been more than just a single CPU, you could have more than one instruction pointer, so one could have two programs.
Correct. Which should hopefully make sense, right? The two CPUs could be doing two different programs, right? Or even crazier, they could be working together in a single program to solve one problem, right? That's how you can get some parallelism into your programs. So the OS is responsible for a couple of different things. It manages the file system. It it manages memory. It manages processes. And then the first one, we have file system, memory, processes. I believe it also manages I/O. So the first thing with like the file system, and this is probably the one that you and I encounter like the most apparently when we're working with the computer, is when you say that you want to open some file, what do you give to say? What do you give to the computer to say, I want to open this file? What do you provide it? Well, yes, but what input? Right, you just give it some text string, right, the path to that file, right? But this file is actually going to be stored somewhere on your hard drive. So what the operating system does is, given where that text string, it takes that text string, right? Then it has some mapping for where that file actually exists on the hard drive. Then it goes to that location on the hard drive, right? And then reads that contents from the hard drive into memory, and then provides those values to you to be able to use, right? I'm super happy I don't have to deal with this spinning magnetic disk to figure out which bytes actually belong to my program, and actually dealing with the reading from that hardware device to make sure that I get what I want. The operating system also manages memory and like the other resources to make sure that they're shared evenly, right? You don't have to worry about when you write your program what other programs are running, right? When you've written your program, have you ever cared where your program got placed into memory at? Or how many other programs were running at that point in time? No, you've always written your program like what? You were the only program running, right? And so you didn't have to deal with, where in memory is my program placed, right? Where are the other programs at? How much space do I actually have available to me, right? Because I can't really act like I own all of memory when I'm writing my program, because there are other applications in there. So I don't have to deal with only having like a fixed amount of space and keep evicting parts of myself to the hard drive and then reading new parts of myself back in. I don't have to deal with any of that, which is really, really nice. The OS also manages processes to make sure that they get equal turns to run on the CPU to get their job done. This is what makes it look like I could have 20 different tabs open up here and be running 5 other applications when really they're each just taking turns one at a time running. And it also manages the I/O devices. So if you want to like read from the keyboard or write to the screen or make the speaker go, the speaker go beep beep boop boop, right? Whatever it does. You don't do that directly. You ask the operating system to do that on your behalf. And so it makes sure that everyone shares these devices equally so that everyone can make use of them. Any questions about these responsibilities so far? Okay, so we'll talk a little bit more in depth about one of them, which is application loading. Right, so you're sitting at your terminal and you type /a.out on the terminal. Your program then starts running, right? But the operating system is the one that actually makes that go, right? And when you type a.out into the terminal, right, you're typing a.out into the shell. So what's going to need to happen next, right? If you were the person designing this process, what would you need to make happen to actually get this program up and running? What would your first step need to be, given that you type a.out on the shell? Locate the instructions, and these instructions are stored where? They're not in memory yet, right? Because a.out, what's it look like? Right? What's the difference between a.out and /home/work/ my file? What's the difference between these two things? Where are they both located at? They're both on the hard drive, right? So your program isn't in memory. So your first step is to do what? You have to go figure out where it's at on the hard drive, right? But the first thing is, because right now, the terminal is the one that's running, not the operating system. The terminal will execute execve a.out. What the execve command means, it means run that program. Or actually, it means replace my memory image with this program's memory image and then start running it. But essentially means run the program to tell the OS to start running a.out. So again, the shell is just a program. So you can have programs that run other programs. Can you think of an example in your life where you encounter programs that run other programs on a regular basis? How about Mimir? Right? What are we doing? We're running programs that run your program and see if the output matches, right? So programs that run other programs do totally happen, and you can also do this as well, right? So you tell the OS to say, hey, I'd like to go run this. Control, start running a.out, so control switches to OS. So like was mentioned, the first thing that we have to do is locate a.out on the hard drive. So great, we found the a.out on the hard drive. What do we need to do next, given that we know where it's at on the disk? We need to put it into memory, right? But where into memory should we put it? Well, I mean, the instruction pointer should point to the memory that eventually should point to the memory that belongs to your program, right? But you probably don't want to copy the current program's that contents in memory to where EIP is, because you would replace the operating system code with your program's code, and you probably don't want that to happen. Yeah. Yeah, right. So locate a free enough section, or locate a free section of memory large enough to hold a.out, right? The OS does all of the memory management, so it knows which locations are free and which are in use, right? Programs themselves can't allocate memory without going through the operating system. So the operating system knows what's in use and what's not in use, right? And it knows this because it keeps track of memory tables that show which sections are in use and which are free, right? So the OS maintains two tables, an in use and a free table, and the in use will tell it what sections are in use, and the free table will tell it which sections are still available to be used. So it can locate a section that's big enough to fit a.out. But notice in that statement, what did we assume that we knew? The size of a.out, right? So do we know that? Have we got that information? So like the next step between 3 and 4 would actually be to read a.out's header. This has info like about a.out, such as its size, where the text section is at, where the data section is at, etc. So it has various bits of information about the program, like its size, where's the text section at, where's the data section at, where is underscore start, right? Where does the program begin at, etc. Right? So we can read that information in. Then once we know how big it is, right, we can go and copy it, pull it out and copy it there. So we copy it into memory, right? Because we know what sections are big enough to fit it. So it's now in memory. What do you do next? What? What does decode mean? Are you talking about like the CPU cycle, the fetch, decode, execute, right? Not quite. So great, you've copied your program into memory, right? Is it running yet? No, why not? Who's still running right now? The operating system is running. So if we want to start this new application, what do we have to do? Say it again? But we are the operating system, right? The operating system has been doing all of this work so far. Well, but how do we go run that section of code, right? Given that we've copied it in there. To that program's start, right? So then you could say something like jump to a.outs underscore start, right? And we know where that is because we read its header file previously, right? But if we just jump straight to a.out's start, right, a.out will be running, but what happened to all of our information? Is there anything that we need to set up before we go and start a.out? Well, I mean, there's not a prologue because we're not calling a function, right? We're running a program. Right, we need to save the operating system state, right? So before we can start running our new program, we need to save the operating system's state, right? Which are going to be like its registers, right? So we save all of its registers. And there's one other thing that we have to do before we jump to a.out_start. Has to do with the registers. Well, again, the OS has already saved the values of its registers, right? So it's saved EAX, EBX, ECX, every single one of them, right? There's something else, though, that we have to do. Not return, right? Well, we have to like wipe the registers, clean, right? So clean them out, because if we don't clean them out, we might potentially be leaking information to this program, right? So a little bit of security thing. And we need to set ESP to the programs to the beginning of the program stack. And then we can jump to a.out, right? So wipe our registers clean, get rid of what we have in like EAX, ECX, EDX before we start that program. And then we also need to make sure that we set ESP first, right, the stack pointer, to the beginning of that function stack. Otherwise, it would be pointing to our stack, right, the operating system stack, which would probably be a bad thing, because then that program could change stuff in the operating system's memory. So like, wouldn't the new program overwrite those registers anyway? Yeah, wiping the registers is more a security thing, right? If you don't wipe the registers, information can leak between programs, right? Which attackers could eventually exploit potentially. Any other questions? Right. Now a.out is now running. All right, so this is what it takes to actually get your application going every time you do a.out or whatever your program's name happens to be on the terminal. Does that make sense? Are there any questions here?
Is the same to go from the operating system to our programs, or from our program to our program?
We will talk about switching between programs in a minute, or probably on Thursday. But there's a little bit of difference, because when the two programs are switching, we're assuming that they're both already in memory, so there's no need to fetch it from the disk. You need to like save the current program state and then load the other program's save state, right? So there's a little bit of differences, but some of the stuff is the same.
And let's say if you have all these tabs open, you have all these applications open, at what point does the computer say, I have nowhere to store these save states while you're running?
Like when it runs out of resources, it runs out of memory, right? But like, you probably would be noticing like a lot of degraded performance long before it actually ran out of space, because what will happen is not all programs that you're running are in memory simultaneously. The ones that it's not using right now, they'll be copied over to the hard drive to make space for something that's running at the moment. But if you're trying to have a lot of programs taking turns frequently, they'll have to keep moving different things in and out from the hard drive into memory, and going to the hard drive is really, really slow. So you'd notice your computer's like, performing poorly or performing slowly. So you might decide to probably close down some tabs or close down some applications that you're not like really needing at the moment, so that you can get better performance with the stuff that you are doing.
So I guess what's the difference between like when you tell an application to quit completely and when it's just kind of like sitting in your application?
So when the application is like actually closed out, it'll make a call to exit, and then the operating system will just kind of like kill it, and it's no longer running. It's no longer to be eligible to be run again in the future. For applications that aren't doing anything at the moment, they'll still get turns, but if they're not doing anything, they might be like, well, I'm not doing anything, just put me back to sleep. And then it'll switch to the next guy in line. So earlier, right, we said that the operating system is a program, right? But we also said that the operating system is the program that loads programs. But if the operating system is a program and the operating system loads programs, how does the operating system get loaded? You see the problem here? If the operating system is the program that loads programs, but the operating system is itself a program, how does the operating system get loaded? But how? If it's going to load itself, right? This is like the chicken and egg problem. Which came first, the chicken or the egg, right? Because if chickens lay eggs, right, well then the chicken could come first and then we get the egg, but chickens hatch from eggs, so the chicken had to come from an egg, right? How do you resolve this dilemma? What? So, but how? It runs a program, right? But if you're going to say there's a program that runs the operating system, well then how did that program start running, right? Then you say, well, there's a program that ran that program. Well, then how did that program get running? Yeah, so that's definitely one of the things that's done, right? So one of the issues with kind of the problem that we're dealing with right now is we're assuming that programs are all stored in what? The programs are stored in, when they're running, are stored in memory, right? RAM. But RAM, like we talked about earlier, is volatile, right? So when you turn off the computer, what's in the RAM gets lost, right? So this program that's supposed to load other programs, can you store it in RAM? No, right? You have to store it in something else. So the way this works is the bootloader is stored in ROM. So it's stored in read-only memory, right? It's non-volatile. So when you turn off the power, what the contents of this location in memory are don't get overwritten. We should also say that the Intel, when it turns on, EIP is set to OX FFFFF. That's 1, 2, F0. Right? So this is where we place the bootloader. Right? So if the CPU turns on and it's going to be at OX FFFF0, right? That's the program that's going to be run at the beginning of the day, right? So that's what's going to be running because where EIP is pointing. So we're going to make sure that at that location in memory, we actually have the ROM set up so that the CPU starts running the bootloader. So your bootloader is running, right, at this point in time. Well, what's the bootloader need to do? Well, so like, what do you think the bootloader's job is to get running? The operating system, right? So we need to run the operating system. That's our job, right? The operating system, when it's not running, is going to be stored where? It's going to be stored on the hard drive, right? So we're going to need to go get the operating system from the hard drive and copy it into memory, right? Now, if you were the designer and you want to make this program set up as simple as possible, where would you put the operating system at on the hard drive? The first thing, right? You put it at the beginning, right? Because if it's not at the beginning, right, it needs to kind of, if it's not at the beginning, it needs to be at some fixed location, right? Because it's not going to be possible to write like a very small program that can fit in your ROM that can do some complex instructions and go find some operating system at some random arbitrary place on the file or on the hard drive, right? So what's going to happen is the bootloader reads the first sector of the disk and copies it into memory, right? Currently at this time there's nothing in memory, so every space is essentially free, right? Because you live in ROM, which is not a part of RAM, so just go into memory and copy it somewhere, probably at the beginning of memory, right? The OS saved itself to this first sector. Right? That's what happens when you install the operating system. It's going to be overwriting a part of your hard drive to go put the OS there, right? It's going to put itself at the first sector, right? We then jump to that. We then jump to the location in memory we copied the first sector to, and execute the instructions that are now there, which again, that's the OS. The OS then loads the rest of itself from the hard drive into memory. Right? Because the first sector is not going to be of the disk is not going to be big enough to fit the entire hard drive, or not going to be big enough to fit the entire operating system, right? So there's only going to be a small portion of the operating system there, and that portion of the operating system will then go and read the rest of the operating system from disk into memory, and then great, your operating system is up and running. Does this make sense in terms of how it's done? Right? This is kind of the reason why it's called the bootloader is from the saying like pull yourself up by your bootstraps. Right? You know, you can't really physically do it, or you can't pull yourself up by your belt, right? But you know, get yourself going. So we get itself started, right, by putting just the first sector in, and then it pulls itself up by its bootstraps by loading the rest of itself into memory, and then great, we're set up and we're good to go. I will see all of you guys in class on Thursday or in office hours if you stop by earlier.
Quick question.
Yeah, just 1 second. Let me just stop the stream.
Okay.